Hey everybody, welcome to the thunderstorm presentation, and we're going to show you a little bit about how thunderstorms work and how to keep yourself safe from them. So we've already learned that how clouds form and how it involves rising air. Rising air is the key to cloud formation, and it's no different with thunderstorms. We've already learned also that cold fronts tend to be associated with thunderstorms, and they would do so because they're driving the air to rise rapidly in a vertical direction. So it's rapid rise of air. This little animation that you're looking at here is courtesy of the National Weather Service, and they have some really good animations that I'm using throughout this video. And when you look at what it's showing us how you don't even need a front to produce a thunderstorm. It can happen just through after like a whole day of heating by the sun, making the air at the surface so it's low density. And when the air at the surface is warming, it's getting less dense. It's rising, it's expanding, cools to the dew point, that's getting us clouds. And those clouds are going to grow taller and taller. And if we think about this as a process as to, when would this happen? Well, you'd need a lot of heating over the course of the morning. And this shows us why afternoon thunderstorms tends to be a much more common thing than morning thunderstorms. So when we look at, well, what's going on inside this cloud that makes it special and different from just regular old clouds? And what we look at is, because these clouds are just towering in terms of their size, they are going very high into the atmosphere. And if you can make a cloud go that high into the atmosphere, you are certainly going to be below the freezing point. So what we're going to get is a combination of different size frozen particles in terms of H2O. And sometimes we're going to get deposition onto ice crystals, and sometimes we're going to get more like something that might have condensed as liquid first and then froze, and we call those ice pellets grauple. And so we have this grauple and ice crystals, and they're moving around due to turbulence in the atmosphere. So they have updrafts and downdrafts, and they're moving all over the place. There's this tendency for the lighter ice crystals to easily lose electrons. So the rapid motion and perhaps some of the collisions that they're making is leading them to lose electrons, and they are gained by the heavier grauple. And so if you lose electrons, you're positively charged, and the grauple is now gaining these electrons, it's negatively charged. Well, then the next thing, as the picture here, right here, is implying, is there's going to be some separation based upon the weight of the object. You notice that the grauple keeps falling in this picture and the ice crystals are rising. And so if we're in a part of the cloud where there's a lot of updrafts and turbulence, it'll easily be able to blow the light ice crystals higher and higher up into the cloud, but it won't necessarily have enough energy to push the grauple up. And so the grauple is falling towards the base of the cloud. So when you look at how this all distributes out through the cloud, you're getting a separation of charge. The top of the cloud will tend to be more positively charged because it has the lighter ice crystals, which can easily be thrust to the top of the cloud. And the middle / bottom tends to have the grauple and the negative charge. Now you do note that there are some positive charges along the base of the cloud in this picture here, and those are going to take place there due to the warmer temperatures that are going to be evident at the bottom of the cloud. They aren't going to be sufficient, though, to balance out the negative charge that is evident with the middle and the surroundings. So, there is a little bit of a measured positive charge at the bottom of a thunderstorm cloud, but the overall charge of the base of the cloud is going to be negative. So what happens if you have this really strong negative bottom of a cloud? Well, what it does is it induces a charge. It induces a charge on what's right below it. And so the surface of the Earth will become positively charged because its electrons are being repelled away. And as this animation is showing, the same effect would happen to you. You would take on a positive charge standing underneath one of these thunderstorm clouds. And this shows us why you are potentially at risk of being struck by lightning, because you are now the opposite charge of what the base of the cloud is showing predominantly. So there should be an attraction between opposite charges, and that's why you would potentially be struck. So the process of the lightning taking place is kind of complicated. There are a number of things that happen. Some of them are not detected by the human eye, but I will show you there are ways of detecting them. So within the cloud, when we look at that middle section, or middle to lower section, you have the accumulation of all of the negative charges with the grapple, and that little bit of positive charge near the base of the cloud. And what we would get is like a stream of the negative charges flowing through, because there are just so many of those negative charges. They are repelling away from each other, and they are looking to balance out the charge in whatever way they can. So there starts to be a flow to the base of the cloud, and then we get over to this image here, where we have what they call the stepped leader. Here is a slow motion breakdown of what it might look like. So you notice how it's branching out, and what we have are these negative charges that are basically only able to sense a short distance in front of them, and so they are basically traveling out, attracted to positive charges, but in the end they don't necessarily follow a straight line, which would be the shortest route to equalize charges, because they're only sensing what is right in their immediate area. So that's where we get the branching out effect. Now, as it gets closer and closer to the ground, you can get an upward streamer meeting up with the stepped leader, and that connection, if that takes place, if you have the charges connecting, can then result in what we're seeing in this bottom picture, which is the visible flash of lightning. So only when we connect those charges that are opposite, and we get the rapid flow of charges from the cloud to the ground, that's when it's heating up the air to a very high temperature, over 40,000 degrees Fahrenheit. And that's going to make the air so hot that it glows, and that's why we see lightning. So I was saying that we had some evidence of this process, and here you see a slow motion camera that is showing a lightning strike, and it shows things that we don't see with the unaided eye. So that the part that you're seeing right about here, there's the stepped leaders, and then finally it makes contact. And one thing that you note when you watch the slow motion is that the light actually is traveling. So the very bright flash that happens is the lightning, and so it doesn't happen till right there. And if you watch it carefully, you notice that it actually travels up from the ground. So only when the connection is made does then the heating of the atmosphere take place as the charges are flowing, and that then lights it from the ground up to the cloud, and there is a lightning strike. So we all know that lightning is associated with thunder, and the connection with there is that thunder is due to the expansion and contraction of the air because it got heated by lightning. So if you have air that's at regular atmospheric temperature, and then all of a sudden you heat it to 40,000 degrees Fahrenheit, that is rapid expansion that is going to take place. But remember, lightning doesn't last very long, so it's gone, and now you have rapid cooling. And so the expansion and contraction of the air causes vibrations in the air, which we perceive as sound, and that is going to be thunder. We know that they are produced at the same moment of time, essentially, because it's the lightning that's making the mechanical disturbance in the air, but we don't perceive them at the same time because the speed of sound is that much slower than the speed of light. So if we wanted to, we could use this to figure out how far a lightning strike was from where we are standing and where we're observing by simply counting the number of seconds that are passing between when you see the lightning strike and when you hear the thunder. If you take that value and divide by 5, you will get the answer to how far was the lightning strike in miles. When you look at the way that flashes can happen, sometimes they're in the middle of a cloud, so it can discharge to itself. You can also get the negative flashes, as they are referred to, which are the typical cloud-to-ground lightning. And then there are also things called positive flashes, which come from the top of the cloud. Statistics show that about 90% of the lightning strikes that hit the ground are negative flashes. So most of the lightning strikes we get are negative flashes. However, it is possible that you get somewhere around 10% of these positive cloud-to-ground flashes. When you look at one of the dangerous things that sometimes is brought up with thunderstorms is you can get a bolt from the blue, as it's called, and that's where it seems like you're not in a thunderstorm, but yet you can still get struck by lightning, and that's where you can maybe get a discharge from the anvil part of a thunderstorm cloud, which is sticking way out and it's kind of far away from where the thunderstorm is actually taking place. And that can be rather dangerous because people don't think that they're in danger, but they actually are. So what the basic rules are, if you hear thunder, you should get to a safe location. And a safe location would be like a grounded building. So if you have buildings with pipes that travel into the ground, any lightning strike there will channel through the pipes and into the ground, and you would be safe inside a building like that. If you look at what the recommendations are, wait 30 minutes after the storm just to be sure, because that's where you can kind of keep your safe distance from something like that bolt from the blue. Now, it's kind of humorous when you start looking at some of the lightning safety tips, like, hey, you don't want to be struck by lightning like this person. And they give some tips on here, like, hey, don't be like Ben Franklin and fly a kite. But there are actually some good tips here, and like the one where if you were stuck in an open area, what's the best strategy? Crouching down and covering your ears. So that's something that actually is worthwhile. And another thing, this get inside a car. That can also be a good tip, because if you are in a car, you are safe, and it is not because of the rubber tires. The reason why you are safe is because if a lightning strike were to hit the metal frame of the car, it would travel around you through the tires and into the ground. A quick thing to remember, if we think about, okay, well, rubber and tires, that should be an insulator. But remember, air is an insulator. Air is not a good conductor of electricity, and that lightning bolt just went through a whole lot of air before it reached the ground. So having that little bit of rubber tire is going to make absolutely no difference to the lightning. So the reason you are protected is because of the metal cage that you are in. And so if you are inside a car in a lightning storm, you want to stay away from touching the metal frame. And these are all good tips, good things to keep in mind as far as being safe when you're outdoors. And then finally, we have some safety tips when you're indoors, such as pretty logical things. When they say don't use a telephone, they are talking about a corded one, because the electrical discharge could travel through a wire and potentially discharge to you in that situation. If you're on a cordless phone, then that's certainly not going to be an issue. So just use some common sense, being inside and kind of doing things where you're not touching the grounded pipes that would potentially be a place where the electrical discharge would travel through. So hopefully you've learned some things about how thunderstorms work and how to keep yourself safe. We'll see you in class.